denoted by small x and the material point is denoted by capital X. So, a way to read this function is the spatial location of a material particle which was initially at capital X at time t. So, this is a spatial location, there is a coordinate. So, now in this we are tracking the particle, okay? We are tracking the particle, the material particle. Usually in fluid mechanics that becomes very tough because there are a lot of particles and they are going to move around a lot. So, what we instead do is we, as again going back to this example, we put our focus on a spatial point. So, let us say the tip of this pen, we put our focus on it and we just keep a track or a bookkeeping of all the particles which pass through this spatial points. Okay. We put our focus on a given spatial point and we keep a track of all this material points that may or may pass. Instead of tracking the material points explicitly, we track the property of the fluid or property of the material that pass through that spatial point. So, it is something like a eyesight in which you are limiting your focus, okay, and then you are saying that okay, I am going to report all the physical properties which I observe through this focus, okay. And we say that the particle, or if you think of this as a particle or this as a particle, we call that as a control mass because we change the particle by controlling its mass. Okay. We have an explicit control in changing its mass. On the other hand, we call this, of course, in reality it is not going to be a single point, it is going to be a collection of points, a collection of spatial points, and we call them as control volume. Okay. So, this is the basic distinction that was made hopefully in APL 106 for you, and the first technique of tracking the particle is called the Lagrangian technique, and the second technique is called the Eulerian. So, these are just names. The essence of that is in one you are tracking the material particles, in the other you are counting the particles or looking at the properties or counting the property of all the fluid particles which may be passing through a given point. Okay. Does not have to be fluid particles, any material particles. So, from this you probably move to what is known as a material derivative. So, imagine there is a river that is flowing from left to right, and then in the river you have injected a dye, okay, and this blue color represents that dye. So, from left to right the dye concentration has a gradient, okay. On left you have very dark blue, on right it is fading gradually. So, there is a gradient in space. Whenever I say gradient, gradient should mean a variation in space. The quantity is not uniform in space, the concentration of dye is not uniform in space. Now, let us focus on two particles, two spatial particles or two spatial locations P1 and P2, okay, and we are going to track the change of concentration on P1 and P2. Okay. One another thing is that this dye is, let us say it is radioactive and it is decaying in time. So, it is changing with space at a given time, and as the time progresses this is going to decay also. Okay. Let us assume, this is just for assumption, and let us track how the concentration of a fluid particle. So, let us say now let us move our focus to a material particle that moves from P1 to P2. How does the concentration of this dye change in that particle? Okay. So, what you are going to see is that as the particle is moving, the concentration is of course going down, but it is going down due to two reasons. One is because at a location it is going to decay since it is radioactive, and the other reason is that it is moving from a higher concentration to a lower concentration space. Okay. So, there are two phenomena which contribute to the reduction in the concentration. Let us represent it with T, this could be temperature also, there is no it is not necessary to think of it as dye, it is just that it is easier to visualize dye with the colors. So, the particles concentration when it was at P1 at some given time T1, it was here and now it is here. The reduction has happened because if the particle had stayed at P1, in even then the concentration or temperature, whatever you want to think about, reduced, but because it moved, it reduced more than what it was going to reduce just by staying at that position P1. So, if I say that the reduction that happened because of the gradient is this. So, this is gradient T dot delta x. Okay. If you do not understand the maths, the dot product makes a lot of difference here. It is not just a multiplication sign, it has to be a dot product. Why? We will look at it probably sooner. Or if you just want to know, you guys know about directional derivatives, right? Do you know what is a directional derivative? Huh? Are partial derivative? But if I want to take a directional derivative in any arbitrary direction, then what do you do? Gradient dot the unit vector in that direction. Okay. So, this you can think about like a directional derivative multiplied with the length that delta x. Okay. So, gradient of t is going to be a vector if t is a scalar, then we want the difference between the values of t between p2 and p1. So, we have to take a dot product with the direction vector p1 to p2, okay, to get that difference, because difference is of t quantity which is scalar. So, difference has to be a scalar, but because we have to get a scalar, that is why we take a dot product. That is not a good way of reasoning it. Okay. The good way of reasoning is just look at what is directional derivative and from there it follows. Okay. So, grad T dot delta x is the difference between the concentration between P1 and P2 at some initial time, but the particle is here. So, whatever particle is here is it is here because at P2 the concentration has reduced due to radioactive decay or whatever also. So, the two quantities contribute to the change in concentration of this fluid particle. So, when you add these two, you get this expression where one is partial t, partial capital T by partial small t plus u dot grad t, okay, where I have written this delta x as u delta t. Okay. Now, again this is just a review, we will look at very rigorously, we will look at how to get this expression. Okay. And this expression, by the way, we called as material derivative in APL 106. Okay. Once this was defined, I am hoping you guys went to Reynolds transport theorem, okay, for which you probably defined the flux of an intensive quantity. Flux is defined as the density times the intensive quantity times the velocity, okay, and then you hopefully defined a system and a control volume. You had a control volume's boundary which we call as control surface, okay, and we have the system boundary. Okay. And then you probably looked at a particular section of this control volume, you zoom in and then you can think of whatever the amount of this intensive quantity coming out of this control volume, that is what we use to define flux. So, this quantity, if you think it is coming with a velocity u, but of course, that u does not have to be perpendicular normal or locally normal to the surface. Let us say this is the local normal. So, u dot n delta t is the height up to which the quantity comes out of the surface, and if the elemental area is ds, then you have u dot n delta t times ds as the volume of this hypothetical cylinder, and when you multiply it with rho times phi. So, if phi is an intensive quantity, that is, let us say something like momentum or energy or whatever, it is quantity per unit mass. Now, we are multiplying it with density. What makes rho phi? Rho phi is quantity per unit volume. Okay. You guys are going to have to focus way more than this. So, if phi is some, let us say momentum per unit mass, then rho times phi is momentum per unit volume. Okay. And then when you multiply it with the volume of this hypothetical cylinder that has come out, then you get the total amount of quantity that has come out of this control surface. Okay. And then once you define the flux, you get the total rate of change of extensive quantity, which is the capital phi, and you write it as sum of change inside the CV plus whatever is leaving CV per unit time. We are going to get into the full detail of this derivation. Okay, we are going to look at in this course the thorough way of deriving this without any jugglery of taking these potatoes and looking at how they are coming inside a control volume, going outside a control volume, and that will require us to look at a little bit of continuum mechanics and continuum kinematics. And then we end up with the expression of the so called Reynolds transport theorem. Now, we can define various capital phi's for which we can define the corresponding small phi's, which are the intensive quantities. So, for example, if capital phi is a mass, then of course, small phi is going to be just 1, and then you end up with something called the continuity equation in the integral form. If you define capital phi as the momentum, then small phi is velocity. By the way, if capital phi is momentum, it's an extensive quantity, it's a quantity of the whole control system or the control mass. So, what velocity do we have? We have a lot of points on the control mass. So, if you imagine a fluid blob, it could be moving with different velocity. So, what velocity do we have there? What is that velocity u? Of which point will that velocity u be? Huh? How do we define momentum of a body? So, that is a velocity of the center of mass, okay. And it is a very important point. It does not make any difference when you are looking at the same fluid, but when you are looking at mixtures which are non homogeneous, then this is an important distinction, that it is the velocity of the center of mass and not just the centroid or the volumetric centroid of this control system. Okay. If we get time, we will see how that distinction plays an important role. But if we write this capital phi as mu momentum, let us say we are looking at the at a homogeneous fluid, and then you get this as the momentum equation, where this F is a volumetric force which would be exerting itself on a volumetric element inside the control mass, and then you have this T ds which will be inside the control volume, and this T is on the surface of the control volume. We will get to all of these derivations thoroughly soon. And then if you define capital phi as the total energy, so the total energy, what will it consist of? What do we mean by total energy here? What will the total energy be composed of? Which different components will be there in total energy? Kinetic energy and potential. But if I have a force explicitly, let us say I absorb the conservative, absorb the forces, conservative forces in that F, then will there be any potential energy? Right. So, what else are we missing? Kinetic energy plus what? In general, what is the other component, or a better word for it? Right, it is an internal energy. So, if you, although this course is going to be about continua, basically we are not going to look at statistical mechanics or atomistics, but if you really think about internal energy, it is like the energy of some fluid which is at rest in a beaker. Okay. So, it is the energy by virtue of which all the particles are moving randomly, which is what you call as temperature. Okay. A fluid at 50 degree Celsius and a fluid at 100 degree Celsius are expected intuitively to have different energies, and what is converting that intuition into maths is the internal energy, to be exact the specific heat. Okay. There is a specific heat of a body, right. If the body does not have specific heat, then it's at absolute 0 basically. Okay. So, there is a specific heat of the body, and by virtue of that we have what is known as internal energy. So, this total energy has both internal and kinetic energy. If you do not want to include your conservative forces F here, then you will have the potential energy as well. Okay. Either you include it here, either you include, so think about it, this is the rate of change of this total energy. So, this is like the power of this F, okay. This is the power of this F. So, you cannot count it twice, you cannot say that this is d by dt of the potential also, and here also you include the potential forces, you have to include it once. Okay. So, if you are not included F the potential forces here, then you need to include them in the potential energy in the definition of total energy. So, using these basics, you probably looked at this in APL 106. We had fluid kinematics. After that, you move to conservation laws, mass, momentum, energy. Okay. And after that, there was integral analysis done, probably a lot of integral analysis problems you guys went through. Maybe not so many problems on differential analysis. Okay. And then there was dimensional analysis, some dimensionless numbers. Then you probably, I don't know, did you guys cover Stokes flow in your APL 106 or do you not remember? That is also valid answer. It is okay. I am going to assume you covered then, but that does not make any difference because we are anyways going to cover this in detail this time. So, we are going to look at Stokes flow, we are going to look at potential flow. I am assuming that there was no time for boundary layer theory in your APL 106, but if there was, then well and good. And then probably towards the end you looked at 1D compressible flows. So, in APL 361 we are going to carve this subsection of that APL 106 part and we are going to go deep inside these things. To be particular, we are going to go deep inside the mathematics of these concepts. Okay. We are going to go and see first how from fluid kinematics you can rigorously derive the conservation laws. Okay. After that, we are going to see how you can really use differential analysis, and although this is a matter of opinion unfortunately in this institute, but if you really follow logic you will see how integral analysis follows from differential analysis and not this way round. Okay. There will be a trick question sometime in your quiz or exam which will show this to you, that usually this is the path followed from integral to differential, but if you really follow logic this is the path. Okay. So, we are going to go deep inside these topics. We are going to look at, in differential analysis we are going to look at solution techniques for PDEs, which I am assuming you guys have done in some of your applied maths courses. Do you guys know separation of variables? So, if you guys know separation of variables, then we are going to look at that and solve some problems using that. I am assuming you guys do not know about asymptotics. No? Have you covered this formally in any course? So, this is also not a formal course in asymptotics, but the fact that we have to look at boundary layer theory means we have to make a formal introduction of asymptotics. Okay. So, we are going to look at asymptotics. Basically, asymptotics mean that let us say you want to solve, for example, this problem. If you guys want to solve, then it is very straightforward for you. Okay. But if I ask you for quicker answer for this problem, okay, it's about some ma'am, I mean attendance you have marked, right? If you don't want to focus you can leave. Okay, I'm okay with that. So, epsilon goes to 0, in the limit of epsilon goes to 0, can you quickly tell me what the solution is going to be? The answer is yes. What is the solution going to be in the limit epsilon goes to 0? Plus minus iota, right? So, there are two solutions. So, you will get this. Will there be plus minus iota or just iota? Iota only. डिसाइड कर लो. नहीं तुम बताओ प्लस माइनस होगा, बस दिस इज मैथ्स दैट यू गाइस आर सपोज्ड टू नो. नो, when the limit epsilon goes to 0, what is the solution of this equation? Plus minus iota. What about this equation? So, you get one solution, although you are required to evaluate approximate solutions of a quadratic equation. Okay, and this if you are hi, कुछ explanation तो दे दो, बैठने दूंगा बट थोड़ा सा मतलब just for formality sake.
Sir, I didn't know the LH.
हाँ, हम अब पता चल गया. चलो बढ़िया. So, in the limit epsilon goes to 0, a naive substitution of epsilon gives you a single solution, although I am asking you for two approximate solutions. So, what is going on here? Okay, even with a simple quadratic, there are tricks that can be made. So, these are the kind of questions that we are going to answer in this course. Of course, we are not, it is not a maths course, so I am not going to look at that, but I am going to motivate boundary layer theory through an example like that. Okay, and believe it or not, that is a standard motivation of boundary layer theory. Mathematically, boundary layer theory is a mathematical concept. Okay, it does not mean you have to have a flat plate, you have to have a flow going past that flat plate, and then you have to have a thin region of viscous effects only, and only then you can call it boundary layer. There are some asymptotics which make a lot of problems uh, solved through boundary layer theory. Then we are going to look at hydrodynamic stability, which I am assuming you guys have no idea about, which is going to make this very interesting. Okay, and given that it comes towards the end of the course, only 3-4 students end up learning it. So, I suppose, and then turbulence if we get time. Okay, in the new curriculum, I think in APL 361 there is a there's space for compressible flows also, but turbulence we are going to hardly cover turbulence. So, there is no space for compressible flows. Compressible flows deserve a different course altogether. Actually, all of these topics deserve a course altogether. Okay, there is a in actual world renowned universities, Stokes flow or low Reynolds number flows is a separate graduate level course, not an undergraduate level course. Potential flow is a separate course, boundary layer theory is a separate course, hydrodynamic stability theory, even in our department we have a separate course, and turbulence we have 2 courses in our department. So, all of these topics are they deserve a course of their own themselves. Okay. The idea of this course is to make you able to understand those courses, okay, because the jump from APL 106 to those courses is a bit too much. Okay, so, the idea of this course is like a bridging course for someone who is aiming to, let us say, take graduate level courses. Now, why is it a core course? That is not a question that I have an answer to. Okay. So, course policy and take home. So, this is how we are going to have our assessments. We are going to have one midterm exam, one major exam or end sem exam. Both of them are going to have 30% weightages each, and then we are going to have 7 quizzes, out of which best 5 we will take. Okay. I have shared this. फ़ोटो लेनी है तो मुझे बता के लेना, मैं नहीं आना चाहता तुम्हारी फ़ोटो में, पता चला कल मॉर्फ होके मैं कुछ और कर रहा हूँ फ़ोटो में, मीम में किसी में. So, I'll try to be outside the frame. Okay, so we are going to have best 5 out of 7 quizzes. There are not going to be any makeup quizzes. So, the 2 quizzes that are there, those are your degrees of freedom. If you have some marriage to attend, you have some function to attend, you have some event to organize, try to arrange it in those 2 quizzes. There is not going to be any makeup quiz. Okay. And this is the snapshot of a, actually it is a snapshot of an old course of study. I do not know what does new course of study say, but this is the standard attendance criterion that we are going to follow. So, hopefully by the end of this course you will learn a few methods of solving PDEs and ODEs. Okay. Reduce a few nonlinear PDEs into nonlinear ODEs. We will look at these kind of tricks also. You will have some idea of how asymptotics work. This is usually called the regular perturbation problem. This is called the singular perturbation problem in asymptotics, and they actually play a role in fluid mechanics, because now again this is very hand wavy at this moment. Okay, but let us say you have a flow past a plate or a body, let us say. Okay, let us say you have a flow past a body. Now, in your APL 106 or in your AMP 262 also, or heat transfer courses also, you have, you know that there is a thin region where viscous effects are important, but outside that region viscous effects are not important. Okay. The singular perturbation problem applies to this region. Okay. And this regular basically this singular perturbation problem, and the way to solve it, when you naively substitute epsilon to 0, then you get the potential flow solution. But when you do the trick of asymptotics, which we are going to look at later on, you get what is known as the boundary layer theory. Okay. So, it is a lot about zooming in and zooming out on your coordinates to solve, to get some approximate solutions. If you do not understand this, it is perfectly fine. I hope once we look at it in detail, you have some idea. Okay. And I mean, I hope for those of you who are interested, fluid dynamics will be less daunting. So, now the fun part. So, this was 23 to 24 semester 1. These are those statistics of APL 361. So, this was the first ECM batch. Okay. It shows the systems are rigged not to show this. It shows 5F, but 3 of those students actually did not attend major. Okay, so once they appeared for remeasure, 2 students ended up failing, and the usual story is around 15% of the class was actually interested. And from my side, the difficulty of exams and quizzes was intermediate. Actually, so this does not apply to you. So, this I have kept for your one senior batch, because I taught APL 106 to those guys, and what I did was in APL 361 as first quiz, I just gave APL 106 first quiz. Even then, this was the performance. Okay, so this is just not even a test of how much you remember. After covering the full recap of APL 106, this is what I gave, and this is what turned out to be the situation. I wasn't expecting this low of an average score, but fine. And these were the average and the max scores in midterm and major. This is very concerning or of great concern. Okay. Such low averages are not usually expected. This is the feedback. Okay. This is the feedback. So, remove this professor, bring someone who teaches with passion like him, but also respects others' careers too. I do not know when I made some poor remarks on their career choices, but looks like I did. But I like that even haters had good things to say about me, that I teach with passion. So, thanks for that. But yeah, as usual, the most of the feedback was no opinion. There was just 50% of participation in feedback. A few disliked long exams, and a few hated that I did not approve of their career choices. The year after that, which is your senior batch, in some sense was better and in some sense was worse. Eventually, one student failed. So, I guess that statistic is better, more appealing. Around 10% of the class was actually interested. So, this I am the percentages I am giving are based on what is the average attendance throughout the semester. Okay. So, in the first installment of this course, it was around 6, 7 out of 40. This time it was less than 5 or 4. Okay. And that I thank for the brilliant course designers of this department, who say that your core job is SD at Microsoft, but then they keep fluids and solid mechanics as core courses. I do not know why. I have stopped reasoning that. But yeah, unfortunately, it is a core course for you guys. So, just bear with me. Average scores were like this, but overall, what I would say is, yeah, I mean, this is some of the feedback. I am going to put this presentation on the course web page, so you can look at this. One thing that I keep getting is showing practical applications of the topic. So, if I had a chance of bringing a portable wind tunnel inside the class, I would show the practical applications of everything that is being done. Whatever I discuss theoretically, and whatever problems we solve, all of them are used in actual engineering design. Okay. I just do not have the luxury of bringing a portable wind tunnel. Maybe someday I will bring, but so far I have not been able to make such wind tunnel. So, yeah, so these are the general suggestions. Yeah, this was very interesting. I am insensitive and inhuman. This was actually very interesting. I don't know. So, overall the participants were more, slightly more. Majority said that the quizzes helped them, which is why I have kept the same assessment for you guys. That is, we are going to have 7 quizzes, best 5 out of 7 quizzes. Okay. I don't know, maybe I should link my blood report to prove that I am human. I am not inhuman. I don't know how to counter that. So, this has been my learning by teaching this course twice. There's a famous saying, you can only take a horse to the water, but you can't make it drink the water. So, I can guide you guys, I can give you whatever number of problems you want, whatever number of practice questions you want, whatever number of exams you want, I am ready to grade them, but I cannot solve them for you. Okay. So, eventually it's your the process of having a thought in your head and then making it flow through your muscles and writing down the maths, that has to be your effort, not mine. So, my commitment is towards the subject and doing justice to the content, and of course, hoping that I'll teach it to you. Okay, I'm not here to put my judgment of your personalities in writing. I'm not going to say that this and this fellow was inhuman or insensitive. That's not my job here. And my personal opinions for your career choices, if inadvertently I end up bashing them in some class, they matter as much as anyone else's. Okay. So, if you have made a career choice, I am assuming it's a well informed career choice. So, why should you care what others think? And if you are not interested in the subject, please remember it's a core course. There are examples of students who did not pay much attention to the course, failed, had to do a self study, suffered through the summers, and then some of them managed, some of them did not manage to pass and had to do it again and then again see me in the next installment. So, yeah, feedback is the key to continuous improvement. So, if you don't feel something is going well, please tell me. Please tell me how I can improve it, because I don't have a badge of being the celebrated teacher of this institute. Okay, so I am open to suggestions, whatever you want. Okay, if you want me to go slow, but have a suggestion of how I can still cover all the topics, I'm welcome. I welcome that. I can actually manage cutting out some topics also. Okay, depending on their importance, which I'll be doing this time. Earlier, I went too much in the detail of boundary layer theory and hydrodynamic stability. This time, I'll try to tone them down a little bit. Okay, maybe have a practical example shown in the class if possible. Okay, so I've already emailed about the course web page and everything. So, are there any questions? Yeah.
So how many quizzes would be before minor and how many would be after minor?
I don't know, man. I have no idea. Maybe 3, 4, and both based on that 4 or 3. Okay, that is what happened in the last installment. Let's see what happens this time. Yeah.
Surprise or announced?
Announce surprises. This will be announced. This will be announced way before, well in time, at least 1 week. Okay, and the kind of quizzes that I give are, so you guys are allowed to bring one cheat sheet where you can write whatever you want on an A4 size sheet, and hope to have it of help in the questions. My TA is laughing because he knows if that's going to be of help or not. But yeah, sometimes those are of help. Like if you are going to solve Navier-Stokes in cylindrical coordinates, I do not expect you to remember all of those lengthy formulae. I expect you to know how to solve those lengthy things within some approximation. So, this course is not going to be a test of your memorization ability to some extent, but of course, to most extent, memorization and understanding, they go hand in hand. To process some information, you have to have that information in your head. Okay, so it's not going to be a core memorization course. It's an engineering course. There is a logical way of attacking all the exams and quizzes, but in my experience, cheat sheets don't help so much. Okay, so yeah. Any other questions? It should be. Is the website not accessible?
Through the link that you mentioned in the email, it's not accessible,
Hmm.
but from your main website.
Okay, I'll try to respond on that email and see what's wrong with the link. Okay, but you have access through my website, right? Through my actual website, you can go to teaching advanced fluid mechanics and then you will be guided to this page. Okay, I am not doing Moodle this time because I think Moodle was down for some time when I was trying to upload a lot of content. Maybe they were updating Moodle or something. So, I am not doing Moodle this time. It is all going to be on my web page only. Okay. Yeah. So, let us begin with our or maybe I should begin here only. Let's go off. Huh. The lights be on a screen. So, let us begin formally with our discussion and we will start with index notation. So, have you guys looked at index notation in any course previously? Which courses? Oh, in APL 106 also you have looked at index notation? So, does this expression make any sense? Does this expression make any sense? Why? अभी intuitively बता दो, you don't have to get down to the nomenclature of things. Mm-hmm. Mm-hmm. So, you are on the right track. So, this expression makes no sense because there are two very important indices in index notation. One is called, as your friend said, dummy index and the other is called a free index. Okay. What is a dummy index? Does anyone recall? What is a dummy index? So, the first rule of index notation, if an index is repeated, it is called a dummy index and it is assumed that it is summed over all its values. Okay. So, basically if I write a correct version of something like what I was trying to write, let us say if I write like this, then which one is repeated here? J index is repeated. So, it is assumed that the J index is summed over all its values, that is without explicitly writing the sigma, it should be understood or implied that this expression is actually something like this. Okay. What about this expression? What about this expression? Huh? So, the reason I put repeated words in quotes is repetition means here that it is repeating twice. Repetition thrice is not allowed by definition of the word repeated whenever this index notation was coined. The reason is if you have it 3 times, then there is an ambiguity. If you follow this rule, then there is an ambiguity. If you follow the rule with the particular meaning of repeated means repeated twice, then there is an ambiguity because which two are you going to repeat? Okay. But if someone meant this repeated in not particular sense of repeated twice, then there is no ambiguity here. But since this was defined with repeated meaning repeated twice, then there is an ambiguity which two are you going to repeat, and so this makes no sense. Okay. J here was the dummy index. Which one is the other index? I, which is called the free index. So, the second rule of index notation is free index should be same on both sides of equal sign. Okay. Meaning that this expression makes no sense. This expression makes no sense. Okay. J is a free index for C, but there is no J appearing on the LHS. So, this expression makes absolutely no sense. Now, this is what is index notation. It is really just this much as far as this course is concerned. If you look at the chapter 1 that I have shared on my website, then you will see that there is an advanced version of index notation in which the indices do not just appear in the subscript, but they can appear in the superscript also, depending on what kind of vectors we are looking at. But keeping that aside, let us look at the motivation of index notation. One motivation of index notation that you guys should be able to guess from this formula is shorthand. It helps us write lengthy expressions in a very small amount of space and convey the same meaning. Okay. So, let us say you have a Cartesian system x 1, x 2 and x 3. Okay. And let us say the unit vectors around along x 1, x 2, x 3 are e hat 1, e hat 2 and e hat 3. Let us say I do a transformation of this, I keep it orthogonal, but I transform it in some sense that now we have some e hat 1 prime, we have some e hat 2 prime and we have some e hat 3 prime. Okay. So, if there is a vector that I define, let us call that vector A. So, throughout this course I am going to denote the vectors with a underline like this. Okay. In the notes you will find them as bold faced small letters. Okay. So, in the notes that I am uploading you will find this vector as bold faced small letter. Okay. So, let us say I write this vector as its components. So, it will be a 1 e hat 1 plus a 2 e hat 2 plus a 3 e hat 3. Now, applying these rules, or to be exact applying this just one rule, I can write this in a shorthand as a I e hat I. Okay. I am expanding the vector along the basis e hat I. I can similarly expand the same vector along the basis e hat I prime. Okay. I can write it as some a I prime e hat I prime. Now, how do I find a I prime in terms of a I? I told that e hat I primes are also orthogonal. So, what do I do to get a I prime in terms of a I's or a J's whatever? What do we do here? Hmm?
We can write EI hat in terms of EI prime.
We can write
EI hat,
e hat I,
okay, E hat
yeah, that is okay.
in terms of E hat I prime.
Okay. How do we do that? From these two definitions, how do we proceed to do that? We take a dot product. So, if we want to write a I primes in terms of a I's, what do we take a dot product with? So, do I do this? Does this make any sense? Does this make any sense or is it violating some rule? it is violating the rule of repetition. I cannot write I here, I cannot repeat this thing more than twice, that is just not going to help. So, if you cannot repeat, the basic idea is to just write a different index, and the algebra will sort out and make you replace some indices if they are destined to be replaced. Okay, that is one way of thinking about it, that if I and j need to be replaced in some sense, then there will be a particular type of expression coming up which will help you replace them. So, what is E hat I prime dot E hat j prime, given that E hat primes are orthogonal? So, both I and j are what? Here I and j are what, dummy or free? Free. So, you cannot say it is equal to 1, 0, 3, you have to give its values for different combinations of I and j's. Okay. So, it is actually 1 if I equals j, 0 otherwise, and we denote it with the symbol. What is that symbol? Kronecker delta or delta ij. Okay. This is the definition of delta ij. Again, this is something that is going to prevent us to write this cumbersome expression and just replace it with delta ij. Okay. So, this when I take the dot product of this equation with E hat j prime, what do I get? A I E hat I dot E hat j prime equals A I prime E hat I prime dot E hat j prime, which I can write as A I prime delta I j. Now, on the right hand side, what is the free index and dummy index? I is what? I is free, I is dummy, I is being repeated, j is free. Okay. We will define if j is free, if we see that on the left hand side also j becomes free, but you can clearly see that it will be a free index on the left hand side as well. So, what does this expression simplify to? A I prime delta I j, A j prime or A j dash. Why? Because this, so this means by definition that it is equal to A 1 prime delta 1 j plus A 2 prime delta 2 j plus A 3 prime delta 3 j. Now, this expression based on the value of j is going to filter out one of these three, and it will so appear that this index will be equal to the value of j simply by the nature of or by definition of delta I j. When j is going to be 1, only this is going to remain and others are going to be 0, j is 2, this remains, others go to 0, and so on and so forth. So, this is basically A j prime, okay. And this is A I times, let us write this E I dot E j prime as L I j. Now, you see how many equations are these that I have written here? How many scalar equations I have written? 3 scalar equations I have written in just this much space. I managed to not write a 3 by 3 matrix, okay, by just writing its components as Lij, and this is basically Aj primes times Lij Ai, and this is the power of index notation. It helps us write very cumbersome equations, vector equations to be exact, as in a shorthand in very small space. Okay. So, there is another way of visualizing this. Okay. There is another way of visualizing this. Let us say I arrange these AJs in a row. So, let us say I write the AJ primes, let us say A1 prime, A2 prime, A3 prime, I arrange them in a row. Okay. Then this becomes a row times a 3 by 3 matrix multiplication. This is A1, A2, A3 and the matrix of Lij's. Okay. Another way of looking at this is you define e hat I prime, e hat I dot e hat j prime as, let us say, instead of small l, let us define as capital L j I, okay, and then you write this expression as L j I a I. Okay. When you are writing index notation, pre multiplication or post multiplication do not make much difference, but when you are going to visualize this multiplication as matrix products, then pre multiplication and post multiplication is going to make a lot of difference. Why? Because now when you do this, then you cannot imagine AJs to be arranged as row vectors, they will be arranged as columns, AJ primes. So, this will be A1 prime, A2 prime, A3 prime times the matrix into the second column, into another column of AIs. The reason why I am giving you this visualization is to show that in some courses you may be shown that, oh, these are column vectors, in some courses you may be shown, oh, these are row vectors. It is really a choice. It is really a choice, it is a matter of convention of a particular field, it does not change the logic of the equation. Okay. The result, end result that you are going to get is going to remain the same. So, choose whatever you want. Throughout this course, I am going to make sure or try to make sure that whatever we, wherever we use the index notation and whatever visualization you guys choose, you will get the same result. Okay. If we do not get the result, that means there is a problem in algebra that I have done on the board and you can point it out. Okay. So, we are going to close this here for today and carry on with this in our next class. You can hand over the attendance sheet to my TA.